Hi, I'm Dr. Incognito. In this video, I'm going to discuss linear independence. Linear independence of vectors. So first, the general concept is easiest to understand in two dimensions. If we have, let's say that's the origin in two dimensions, and we have two vectors, u and v, then these two vectors that I've drawn here would be considered linearly independent because they lie on different lines. Basically, what that means is that you could theoretically get to any point in the plane, say that point there, by doing some linear combination of u's and v's. To see that, if we extend the u line a little bit, and we extend the v line a little bit, then we can make a parallelogram involving these two extended lines and this dot. So if I make a dotted line here parallel, and here parallel, then what we see is that this longer vector here, let's call that a times u, and this longer vector here, let's call that, the shorter one is v, the longer one is b times v, then we can see that this point right here can be arrived at by doing a times u plus b times v. So again, with these two vectors, u and v, that were not pointing in the same or opposite directions, they were pointing in completely different directions, we could get to anywhere in the plane. These two vectors would be an example of linearly independent vectors. The span of these two vectors, then, would be a plane. It would be a two-dimensional space. It would be a plane. Whereas if we look at this situation, suppose this was u, and suppose v went, let's say, in the exact opposite direction, then these two vectors are both on the same line, and the only points you would be able to get to by doing any combination of u and v, the only places you would be able to get to are on this line. You would never be able to get to a point that wasn't on the line as a combination of u and v. These two vectors are called linearly dependent, and their span of uv is just a line. It's the same as the span of either just u or v. So the idea of linearly independent vectors beyond two dimensions is that when vectors are linearly independent, then each one contributes a dimension towards the span. So if we have three linearly independent vectors, then we would have that the span of UVW would be three-dimensional. If these were linearly independent, then the span would be three-dimensional. And this will happen if the three vectors uv and w do not lie in the same plane. If they, two of them will lie in the same plane, and then the third should be a vector off in space not on that plane. Now, technically, the mathematical definition kind of obfuscates this main idea. It is that n vectors, v1, v2, up to vn, are called linearly independent if the only way to combine them and make the zero vector, so if you combine them, c1, v1, a combination, c2, v2, a linear combination, if you combine them, cn, vn, and you get the zero vector, the only way for that to happen is if all of the coefficients are zero. This happens only when, so linearly independent, if this equals 0, then C1 equals C2 equals C3, etc. equals 0. All of the coefficients are 0. It's always possible to make a combination equal the 0 vector. That would be, you could always take all coefficients equal to 0. The vectors are called independent if that's the only way to make a combination equal 0. If we look at these two vectors, combination of them equaling the 0 vector, that will only happen if we take 0u plus 0v. Whereas here, in this case, it looks like maybe something like u plus, I don't know, maybe u is just, let's say they're the same length, so in opposite directions, then u plus v would be the 0 vector. So here you have a combination of the two vectors making the 0 vector. Here, if you take some u's and some v's, and the coefficients are not 0, you will not ever end up at this point. Once the u's take you away from it, the v's will never bring you back to that point. So, linearly independent vectors, the only way for a combination to give you the 0 vector is for all of the coefficients to be 0. So let's try an example of that. Let's take 3 vectors in R3 and see if they are linearly independent. So let's take v1 to be the vector 1, 0, 1 in R3, v2 to be the vector 0, 1, 1, and v3 to be the vector 2, negative 1, 1. Let's take those 3 vectors. Is the set v1, v2, v3, is this a linearly independent set? Yes or no? So we construct the following: c1, v1 plus c2, v2 plus c3, v3. We set that equal to the 0 vector, and we ask, is this possible with c1, c2, c3 different from 0? With any one of them different from 0? So in this example, this is c1 times the vector 1, 0, 1 plus c2 times the vector 0, 1, 1 plus c3 times the vector 2, negative 1, 1 equals 0, 0, 0. Now we can add these vectors together. This is the same as c1 plus 2c2, c2 minus c3, c1 plus c2 plus c3 equals 0, 0, 0. And this gives us a system of 3 equations in the 3 unknowns, c1, c2, and c3. The first equation is c1 plus 2c2 equals 0, from looking at the first components. The second equation is c2, let me leave a little space there, minus c3 equals 0. And the third equation is c1 plus c2 plus c3 equals 0. So we can write this homogeneous system in matrix form: 1, 2, 0, 0, 0, 1, negative 1, 0, 1, 1, 1, 0. Where this is the C1 column, this is the C2 column, and this is the C3 column. So let's solve this system. One solution will clearly be C1 equals C2 equals C3 equals 0. Are there any other solutions? Are there any non-trivial solutions? So we row reduce the matrix. 1, 2, 0, 0, 0, 1, negative 1. If we subtract here, subtract row 1 from row 3. So 1 minus 1, 1 minus 2, 1 minus 0. 1 minus 1 is 0. 1 minus 2 is negative 1. 1 minus 0 is 1. And then we notice that row 2 and row 3 are negatives of one another. So if we add row 2 to row 3 gets zeroed out. So we have 1, 2, 0, 0, 1, negative 1, 0, 0, 0. And this is a row echelon form of the original matrix. It's not reduced row echelon form, because reduced row echelon form, we could make this 2 here into a 0 by subtracting off. But to answer our question of linear independence, what we see here is that there is a leading one here and a leading one here. And in the C3 column, there is no leading one, so C3 is a free variable. So our solutions are going to be C3 equals T. It's a free variable. Then C2 will equal C3, which is T again. And then C1 is equal to negative 2C2. So C1 is negative 2T. The important thing is that once we see that C3 is equal to T, then there are infinitely many solutions to this system. Okay, the homogeneous system here has either one solution, the trivial solution, or infinitely many solutions where the parameter comes in. So here we have a situation where there are infinitely many solutions, and so therefore these three vectors are not linearly independent. There is a non-trivial solution to this equation. Let's just write down one of them. If t is equal to 1, then that gives that C1 is equal to negative 2, C2 is equal to 1, and C3 is equal to 1. So in other words, if we take this vector plus this vector, so V2 plus V3, and then subtract twice V1, we will get the 0 vector. Does that make sense? If we add these two and then subtract two of those, we should get 0. Let's just look at that. If we add these two, we get 2, 0, 2. 2, 0, 2 minus two of those is the 0 vector. So you can see that these two vectors would make a plane, and then this vector would be in that plane, because it would be this one plus this one divided by 2, half of it. This one plus this one times half would give you that one. So half of this one plus half of that one would give you this one. So this one is in the plane spanned by these two. And the system, the three vectors would be considered linearly dependent. No, they are dependent. Linearly dependent. Okay, so there's a little example and the definition of linear independence. Thank you for watching. I hope this video was helpful.